It's my pleasure to chair this session. Welcome you all. And we have 4 speakers in this session number 9. And after that, we have interesting programs. So my request to all the speakers is to stick to your time, kindly. So first speaker is our former student, Dr. Pooja Singla. She will be speaking on group determinants and representation theory of finite groups.
Thank you. Thank you very much for giving me this opportunity to visit IMSC at this occasion and meeting all of you. I want to say that coming to IMSC as a PhD student was, the best thing that I feel. Very humbling coming here. Coming all the way from Punjab to this place was not easy in the beginning, but I would say Chennai, math science was so, helpful in all aspects. I'm really grateful for that. And I hope I'll keep on getting more and more occasions to visit math science again and again. Okay, so I'm going to speak about this topic, group determinants and representation theory of finite groups. So this is I'm not talking about my work in this talk. It's basically about talking regarding the history of representation theory from how it originated. Many people who work in even representation theory of finite groups don't know about this. I came to know after finishing my PhD, and I feel that it's something good to know this. And I hope it will be good for students to know it beforehand. So throughout this talk, G is a finite group, and so let's list the elements as A1, A2, so on AL. Okay. Given each element of the group G, I consider corresponding variable, and let's call this X A1, A2, AL. Okay. Then let's write this matrix associated with the finite group G. Its ijth entry is X AI AJ inverse. Notice G is a group, so AI AJ inverse is an element of G. So this is a variable, right? So these are matrices. This is a matrix with all entries as variables, okay, determined by the group G. Now, group determinant of G is determinant of this matrix. Okay, we will be denoting it with theta G. So throughout this talk, you will see this notation theta G in this talk. So as an example, just to keep it in mind, so for example, let's take G to be Z mod 3Z. Okay, I have 3 elements. Let's call this one A square. Okay, I'm just reordering, writing these elements x1, xa square as x0, x1, x2. And if you write this matrix Ai Aj inverse, this is the matrix associated with the group G, and by theta of this group determinant of Z mod 3Z, I just mean determinant of this matrix. For the people who have seen circulants of order n, they may be able to connect with it. These matrices associated with Z mod nz give you circulants of matrices. But for us, that's not important, okay? So group determinant is determinant of this matrix. Now, so group determinant, notice one thing, that this is a polynomial in these variables xai's, right? With integral coefficients, because it's just determinant, but I'm viewing this as a complex polynomial with this in these variables, okay? So the question that we are going to discuss is what is it's a complex polynomial, what is its decomposition into irreducible polynomials for a finite group G? Okay, how does group determinant decomposes into irreducibles? That's a question that we would like to ask. Okay, so for Z mod 3Z, I already gave you the group determinant, and it's easy to see that it has this decomposition, right? All of these x0 plus x1 plus x2, these are irreducible degree 1 polynomials, and this group determinant decomposes like this. We are interested in asking this question for any finite group G. Okay, the easiest finite groups that we think about are Z mod nz. So the first result regarding this was given by Cremona. So they were looking at these circulant matrices, came from Catalan some work. So in 1856, Cremona proved that group determinant decomposes like this. So x0, so if you relate this is how even the previous decomposition is relating to. Here these zetas are primitive nth root of, is a fixed primitive nth root of unity, and it gives a complete decomposition. This is not a difficult proof at all. One can do some matrix multiplication. I mean, looks, it's just a determinant polynomial, and one can do some tricks, easy tricks to get this. So this does for Z mod nz. Okay. Now the next question comes, I know for Z mod nz, what about for abelian groups? Whenever we do something for finite groups, this is how we proceed. We do for cyclic groups, then we do for abelian groups, and then we go for non-abelian groups. Dedekind, for some work in algebraic number theory, required this group determinant decomposition. Okay, so then, and for him, these groups were finite abelian. And so he started looking at this G is finite abelian group, and he came to this group determinant decomposition problem. And he found a complete decomposition here. And so let me just say what he found. He realized that this theta G again decomposes as degree 1 polynomials. Okay, and he could say what are exactly the coefficients here. Coefficients are given by what are called linear characters or group homomorphisms from G to C star. Okay, so if you see the coefficients, he explicitly gave the coefficients, and all of these are distinct polynomials. So basically when he looked at these, he observed that group determinant for abelian, finite abelian group decomposes as degree 1 polynomials, and all of these are distinct. So these have power also 1. Okay, so this naturally led him to ask whether this will always be the situation for any finite group. Okay, now are factors always linear? Are factors always distinct? These were the natural questions that came to his mind. And then he started looking at, okay, for abelian I know the answer, let me work with the first non-abelian group. And first non-abelian group is S3, symmetric group over 3 letters, right? And he realized that when he looked at this theta S3 decomposition, he actually got this decomposition. So he got a degree 1 polynomial, another degree 1 polynomial, and then he got a degree 2 irreducible polynomial. He could show that this is an irreducible degree 2 polynomial, and it occurs twice in the decomposition. So that is something different from the abelian group case. And he also worked out quaternions case, and there also he got some higher degree polynomials with higher multiplicity, and he became curious. He didn't know how to go about it. Okay, but the question that his underlying question was, for a general finite group G, what are the irreducible constituents of theta G? What are the degrees? What are their powers? Questions like that. So he asked his student Frobenius to think about this question. He said, here is the problem that I am not able to figure out. Here is S3 decomposition for quaternions. This is what is happening. Can you tell me what happens? Okay, so this was done. He did it in 1880. Okay. In 1896, Frobenius solved it. He gave the complete decomposition of this group determinant. To do this, what he did, he generalized the notion of characters of finite abelian group. He defined the notion of what is called representation of a group. Okay, so let me just quickly go over the definition so that I can tell you the final result. So if G is a finite group and V is a finite dimensional complex vector space, by representation of G, we mean a group homomorphism from G to automorphisms of the vector space V. Okay, by dimension of the representation phi, we mean its dimension of the vector space V. And notice one-dimensional representations, what that I called as characters, linear characters, are one-dimensional representations of group G. So it is really generalizing that notion. What we were looking at linear characters for the abelian group are, now we are looking at all the homomorphisms to GLV. Okay. I also need what's called irreducible. For that, let's look at sub-representation. Given a representation V of the group G, by a sub-representation, I mean a subspace which is invariant under the G action. Okay, if I have a V with G action through phi, then I look at the invariant subspace. And I say that a representation is irreducible if it has no proper sub-representation. Okay, only invariant subspaces are the zero subspace or itself. There is nothing in between. For example, one-dimensional representations are always irreducible, right? Because you cannot have anything proper in it. And two representations are called equivalent. So if I give phi1, v1, phi2, v2 of a fixed group G, then I say these two representations are equivalent if there exists an isomorphism T from v1 to v2 such that it commutes with the G action. Okay, so by that I mean phi2G T is T phi1G for all G in G. Okay, this is not very important, I am just writing it here for the completeness. Okay, now let's use this notation IRG to write down set of inequivalent irreducible representations of a finite group G. Okay, so of course the question is that whether this set is finite. It turns out that it is finite. The cardinality of this set is equal to the number of conjugacy classes. So it's okay. I can write rho 1, rho 2, rho k is a set of inequivalent irreducible representations of G. You can do that. And then Frobenius, what he proved was, he wanted to give the complete decomposition of group determinant, right? So this is what he proved. He said theta G is the same as determinant of, here rho varies over irreducible representations. Rho G's are matrices, okay? This is a matrix of dimension rho, okay? So xg rho G is also a matrix, and then I am taking a summation, right, of these matrices of dimension rho. I can look at determinant of this matrix, right, and raised to the power dimension rho. Yes, and this product is theta G is what he proved, and what he, this is also a complete decomposition into irreducible, because in the proof he ended up proving that these are all irreducible. This determinant is irreducible. Okay, and then dimension of rho, how many times irreducible occurs. Not just that, he also proved if rho 1 and rho 2 are different, these are distinct irreducible polynomials. So he got a complete decomposition using the representation theory. He proves that given a finite group G. So let me just say quickly that what he basically proves in modern language of representation theory, he decomposes the group algebra as a product of endomorphism algebras of the representation spaces, and then he looks at how the summation AG acts on the group algebra, what is the determinant of that under multiplication, and then proves this irreducibility and distinctness of the factors. That's what goes into proving this. Okay, so decomposition of theta G requires, so what are all the finite dimensional inequivalent irreducible complex representations of G? That is what basically he came to this question, right? So this initiated representation theory of finite groups. Now, of course, he proved this theorem, but that's now given question turns out to be, given a group, how does it decompose? Can you find complete decomposition? Which means one needs to find out all the representations. Okay, so I should say that this is a problem that still is not done. Many times I have talked to people, they say, oh, these are only finite groups, we should know everything about groups, so we should know all the representations of finite groups. That's not true, we still don't know representations of all finite groups. Okay, so let me give you, so in this last slide, I think I'll be finishing much earlier. Let me give you some groups where we don't know, okay, and these are the groups that I am interested in working on. So these are some examples where we know how to find the representation, some cases where we don't know. So first case is symmetric groups. 1930s Young gave us complete description of all irreducible representations of Sn. Very nice description, you can write even the matrices very nicely. GLN Z mod PZ. This was, character tables were given to us by Green in 1955. But I should say, when it comes to writing the representations precisely, so remember, in theta G decomposition, we are writing the full matrices, rho G. Okay, these are not only the characters. So writing the matrices rho G, that's hard. Okay, so even for GLN Z mod PZ, it turns out to be a difficult problem. Okay, now for the next class that generalizes these groups is GLN Z mod PKZ and GLN FPT mod TK, right? Instead of Z mod PZ, now I'm thinking of commutative rings. And I've started asking, okay, what are the representations of these groups? Finite groups, easy looking, but actually we don't know these representations of these groups. If you take K to be greater than equal to 2 and N to be greater than equal to 3, we don't even know how many conjugacy classes these groups have. Okay, so we don't even understand those problems. So we don't know that, we don't even know how many are there. And we don't know the numbers, dimensions, for certain class of representations, we do know. Their character tables, for certain cases we know, but not in generality. Okay, so more generally, one can ask this question for GLN with entries coming from a finite commutative ring. Okay, so these are whatever I've talked about, Z mod PZ, Z mod PKZ, those are examples of finite commutative rings. But in general, finite commutative rings can be much more complicated than these are. Okay, so then we have no idea as of now how to find the representations of these groups. I think I'll stop here.